I'd like to start with questions. If you guys have questions on things, homeworks or whatnot, Michael? Yeah. Yeah. Yeah, it felt like you guys spend so much time on those. It should be weighted more than just 1 point apiece. You know what I mean? Anybody else with questions, homeworks, or otherwise? Yeah, Paulo.
You do. Oh, I think it was 5.
5 on.
5 on the integrating rational functions.
Okay, perfect. Yes, we can do that. So we're looking at this one right here then at the bottom that runs onto 2 pages, right? Okay. So I recognize, or when I look at this, I notice the degree of the numerator is greater than the degree of the denominator, so I would want to use polynomial division here. Since the denominator is monic, I'm going to do synthetic division because it's faster, and given the option, that's always what I would choose. So remember, when we do that synthetic division, we read from right to left, and it's remainder, constant, and then coefficient for x, and so on and so forth. So I'm going to rewrite this integral from 1 to 2 as x minus 3 plus 1 over x plus 2 dx. The integral of x is going to be x squared over 2. The integral of negative 3 is negative 3x. And then to integrate 1 over x plus 2, that should be a u sub. So u will be x plus 2, and du will just be dx. So that's going to be the the integral of 1 over u, which is going to be the natural log. So far, so good. And now it's just time to do our substitution. So we have 2 squared over 2. That's going to be 4 over 2, or just 2. 2 times negative 3, that's negative 6. And then log of 4, and then minus 1/2 plus 3 minus log of 3. And then from there, we're just, thank you. We're going to just be combining some like terms. So we have 5, and then minus 1, and then minus 1.5. And then log of 4 minus log of 3. I know I can use my properties of logarithms to rewrite that as a quotient. So that gets me to A. Finn, I have a early dismissal pass for you here whenever you're ready. Nate?
Could you just go over really quickly how to do synthetic division again? It's been like 2 years.
Yeah, synthetic division. Paulo, you're happy though?
Yeah.
Okay. So the idea here, so if I have like something like this that I want to do synthetic division with, what I do is I want to start by setting the denominator equal to 0, and then solve that. That's the number that's going to go on the outside. And then the coefficients here are going to be the numbers on the top. But notice here how I go from x cubed to x. So I need to include a 0 term because there's a 0 coefficient on the x squared term. All your terms in your polynomial need to be accounted for, even if they have 0 coefficient. So that's the setup. We start by bringing the first number down. And then we multiply the number on the outside to the number on the bottom. We write it in the next spot, and then we add down. And then we just keep repeating that process. Until you finish. Does that look familiar?
Yeah.
Jog your memory? Yeah. Yeah, I know, no problem. Happy to do another example if we need it. No big deal. I know you do that a lot in, Algebra 2 and pre-calc, so I don't want to belabor it if it's something that, like, you've done a lot of practice on. But if you need another refresher, happy to do that kind of stuff. No problem at all. Okay. Who else with questions from homeworks or whatever? Okie dokie then. So today we're going to finish up chapter 6. We're going to do section 6.4 and 6.5. They're both rather small sections, so shouldn't be a big deal. So section 6.4 is about applications for integrals. One specific application is the calculation of work, specifically like work in a physics setting. So those of you that are in a physics class or have taken a physics class, this should come as, or should see some familiar concepts here. But I'm also going to do some examples of like thinking about integration as like a general accumulation function, which is what we're doing here, but it's just like a more broad application rather than specifically this physics application. So Newton's second law, so Newton's a physicist. He has 3 laws to describe motion, or really forces. So the first one is that force is equal to mass times acceleration. In a calculus setting, you might say then that force is equal to the second derivative, or mass times the second derivative of position. Remember that position, velocity, and acceleration are each derivatives of the previous one. And then work is the amount of force applied over some distance. So we would say that work is equal to force times distance. And typically we measure forces in newtons and distance in meters. So the unit for work is the Newton meter, or what we call the joule. Again, some of this is just like physics background unit stuff. But this is the main 2 ideas is just that like these are kind of going to be our 2 basis formulas that we're going to be building. So in some ways you could think of work as just mass times acceleration times distance, right? Because we're just substituting the formula for force in there. So in your physics class, these calculations probably would have been rather simple. Like how much work is done by lifting a 1.2 kilogram book off the floor to put it on a desk that is 0.7 meters high. So the work there, the mass is 1.2. The acceleration is the 9.8 from gravity, and the distance is 0.7. There's not really much to do there. You're just plugging some numbers into a formula. How much work is done by lifting a 20-pound weight off or 6 feet off the floor. Again, 20. Now we have to be a little mindful. Notice that this is in pounds and feet. So I'm going to use that other gravitational constant. I think it's 32 in feet per second squared. So you just, again, you're just plugging it in, right? If force is constant, it's a piece of cake. It's just like an Algebra 1 plugging stuff into a formula kind of problem. But what if the force isn't constant? What if every time you move the object, the force is changing? So now what we're talking about is having to do a separate or a separate work calculation for each little tiny increment, and adding up all those little tiny increments, where every time the force changes, we're going to do a new work calculation and add up all those little tiny calculations to get the total amount of work. Oh boy, this sounds a lot like a integral, and that's exactly the idea here. So what if we have some particle that is located x feet from the origin, and a force of x squared plus 2x pounds acts on it? How much work is done moving it from x equals 1 to x equals 3? So here we can see the force is not constant because it's changing with the position of the particle, right? So what we're going to do is we're going to think about this still as like mass time, or force times distance, right? So the force in this case is the x squared plus 2x, and the distance is still going to be dictated by going from 1 to 3, but because the force is changing on each time, what we're going to do is we're going to calculate the force for just some little tiny sliver of distance, a dx, and we're going to add up all those little tiny slivers of dx all the way from 1 to 3. So that's what the integral is saying here, right? Which we're just going to take like an infinitely small sliver of that distance from 1 to 3, calculate the work done over that distance, and do that, add up those infinitely many slivers, and that'll give us our total amount of work. So it basically becomes this problem, which should be an easy integral for us to do, right? The antiderivative of x squared is x cubed over 3. The antiderivative of 2x is x squared. And then we're just evaluating from 1 to 3. So when I do that, I get like 16 2/3 foot-pounds. So notice that this is still just force times distance, right? We're just doing that calculation for a little tiny sliver of the total distance, and we're doing infinitely many of those calculations, and then adding up all those works done over those little tiny slivers that we're taking. But it's still just force times distance, right? Is everybody okay with this? It's kind of the easiest version of this type of a physics problem from a calculus perspective, is where you're given the force function, and it's just like, okay, I'm just integrating that over some dx, and we're done. Another fairly common presentation is has to do with like springs. So Hooke's law is a law that states the amount of force required to maintain a spring stretched x units beyond its natural length is proportional to that amount you've stretched it past its natural length. So in the case of a stretched spring, force is equal to k times x, where k is like the spring constant. It's something specific to the spring you're working with. If you have a really heavy spring, k is going to be really big. If you have like a really thin spring, K would be, quite small. So let's look at an example here. So we have a force of 40 newtons is required to hold a spring that has been stretched from its natural length of 10 centimeters to 15 centimeters. How much work is done in stretching the spring from 15 centimeters to 18 centimeters? Well, we're still going to be calculating work as force times distance. But in this case, that force is like kx times d. So first order of business is to find that k. Everybody's okay with that? So that's what this is going to be given for us. So if I know force is equal to kx, we can say 40 is equal to k times. Now what is the distance here that the spring has been stretched past its natural length? 5 watts, though? Centimeters. Newtons is measured as meters, so I do have to do a unit conversion here. I'm going to choose to write that 5 centimeters as meters. So you got to be careful about that. Your textbook in particular is not kind with you about units, so you do have to pay a little bit of attention there. Remember, newtons, everything has to be in meters and kilograms. So if I do that, I get k is equal to 800. So now we have that right over here. So now we can basically say this, right? So as a calculus student, we're going to have force, or the integral from, we're going from 15 to 18, but those again are written as centimeters. So what do I want to do there? I need to make sure I do a unit conversion, but I'm not really stretching it from 15 centimeters to 18 centimeters. I'm stretching it from 5 centimeters past its natural length to 8 centimeters past its natural length. So my bounds of integration really should be those guys, right? Is everybody okay with that? Because 10 is like our 0, right? So if we're stretching from 15 to 18, it's really stretching from 5 to 8. But those are in centimeters, so really we want those in meters, so divide them both by 100. Is everybody okay so far? Okay. And then we have 800x dx. And now it's just integration time, right? Remember, this is just force, and that's distance. So it's now integral time. Everybody cool? I'm going to skip the grinding this out by hand, if that's okay with you guys. We're just going to worry about the setups until the integration gets like, maybe it's a tricky idea for like the by hand integration, but this is pretty trivial. All right. So let's look at some setups that are a little bit more complicated here. So here we have a 200-foot cable is 100 feet long. Or I'm sorry, 200-pound cable is 100 feet long. It'd be weird to have a 200-foot cable that's 100 feet long. And hangs vertically from the top of a tall building. How much work is required to lift the tape or the cable to the top of the building? So notice that the force is changing each time you pull a little section of cable up. The remaining cable dangling off the edge of the building weighs less than it did before, right? So I'm going to start by just kind of drawing a picture to kind of inform what I'm doing here. So I'm going to draw myself a building, and then like here's my cable hanging off. I know that this is like, I'm going to start at 0 and go down to 100, right? So I'm going to have like any little tiny section of this is going to be like my delta x. And I'm going to pick like some specific x here. What I need to do before I start, though, is figuring out how much each little section of cable weighs. So how much does any section of cable weigh? Yeah, like 2 pounds per foot, right? So again, if I think about work as force times distance, or I guess this is worth mentioning here. In physics, there's a difference between pounds and kilograms, right? Those of you that are in physics probably remember this. What's the difference between pounds and kilograms? One of them is a mass, kilograms. The other is a force, pounds. So even though we use them both to measure weight, in physics, pounds is a force as opposed to kilograms, which is a mass, which is not a force. So this already has the gravity factored into it because it's measured in pounds. Worth stating that, because if you haven't been in a physics class, that part is totally lost on you. I want to state that for everybody. So that's nice in that we're doing this in pounds, so we don't have that extra gravity piece to account for. So basically, it's going to be, the force is just going to be 2 times x, right? However much you're pulling up is going to be, or the distance you still have to pull is going to be 2 times that is going to be the mass, or the weight of the cable, which is the force, right? Okay, well that's it, right? We're integrating then from 0 to 100, 2x dx. We're done. Because it's easy here because the force on the cable is directly related to how much still you have to pull. Does that feel okay there? All right. This is the worst type of problem you'll see in this section. So here it says a tank has the shape of an inverted circular cone with a height of 10 meters and a base radius of 4 meters. It is filled with water to a height of 8 meters. Find the work required to empty the tank by pumping all the water to the top of the tank. And then it tells us the density of water is 1,000 kilograms per cubic meter. So what does this description already kind of sound like to you guys? Sounds like a related rates problem. Guess what's a very common presentation in a FRQ on the AP exam? A related rate problem in combination with like one of these work accumulation problems. So it's a very common, those pair together really nicely, where we calculate the amount of work needed, to do this, to empty the tank or whatever. Okay, so I'm going to start by just kind of drawing myself a picture of what's going on here. So there's my cone. There's my water. Everybody okay with this so far? So just kind of drew in what we know. I'm going to go ahead and calculate the radius of the water right away, because I know that, you know, if we talk about work here, so the force times distance is just going to be mass times acceleration times distance. So I need to find that mass, I'm going to need the volume. So I'm going to need that radius, I think, to start. Now, let's think about what's going to be changing, though. Right? At some point, what we're going to be doing is we're going to be talking about, like, taking out like a really little tiny cylinder here. And we're going to be moving that like X units up, right? So the remaining height of the water is going to be like 10 minus X. Can you guys see that? So when I try to find the radius for the water, you know, we'll say the radius of the water over the height of the water is equal to the radius of the cone over the height of the cone. So the radius of the water is what we're going to be looking for. The height of the cone at any time is going to be 10 minus x. Or I'm sorry, the height of the water. And the radius of the cone is just 4, and the height of the water, or the height of the cone is just 10. So the radius of the water is going to be 4 over 10 times 10 minus x. Everybody okay there? So the volume for the water, the volume for a cone is 1/3 pi radius of the water squared times the height. Oh, I'm sorry, it's not a cone, right? The section of water that we're moving is a cylinder. My apologies. So it's just pi r squared h. Everybody's okay? So I'm going to reduce that 4/10. And then the height of my cylinder is delta x, right? Yeah, I guess. So that's going to turn into 4 pi over 25, 10 minus x squared delta x. So that's calculating that little cylinder there. Now the mass of that cylinder is going to be 1,000 kilograms per meter cubed times that. So that comes out to be like 160 pi So my force then is the mass of that cylinder times gravity. So that's going to be about 1568 pi times 10 minus x squared delta x. So my work then is going to just be that force times the distance, right, that we're moving. Okay, and we're moving this water from 2 meters initially to 10 meters at the very, very end. So the first cylinder has to move 2 meters and the last cylinder would have to move 10 meters, right? Everybody's okay with that? So we're going to be going from 2 to 10 of 1568 pi times 10 minus x squared. And then the d is just going to be that x that we drew in there, delta x. Or I'm sorry, now it's dx now. Right, when we're doing the integral, the delta x just turns into a dx. And now it's just grind time, right? What do you guys think? How would we do this integral by hand? Let's take that 1568 pi out front. But how are we going to integrate the 10 minus x squared times x dx? Yes? You can, I wouldn't. It'll be a double u sub, because when you set u to be 10 minus x, then you still have the extra x coming in, so you have to turn that into a u also, and it's not going to really get any prettier for you. I would just FOIL out the 10 minus x squared and then distribute the x through. But what you could do, John, what you're saying to do, you could do. I don't think it's going to make life any easier, though. Sometimes the simplest way is the easiest way. Like, let's just try to turn this into a polynomial. Particularly since the FOIL isn't too bad, right? That's a pretty easy thing to FOIL out because it's just quadratic. Or degree 2 thing. It's not like degree 5 or something. In that case, definitely I would be u-subbing as you suggested, John. But here, because the degree is so small, it's easy enough to just multiply it out. If it was degree 6 or 7 or something, well, no bueno. So now it should be fairly easy because it's just a polynomial to integrate. So we'd have 100x squared over 2 minus 20x cubed over 3 plus x to the fourth over 4 from 2 to 10, and then it's just grind time. Does that feel okay? I also want to do like one of these accumulation free response questions. I tucked a couple of the, I think there's 5 of them in here. They're going to basically be using the same kind of principles, but these are not necessarily physics specific. The AP doesn't love physics specific problems because it's requiring like extra instruction that you not necessarily have as an AP physics or AP calculus student. So they tend to like these kind of accumulation problems, but it's the principles are still kind of the same. So I'm going to do number 2 here. It says, when a certain grocery store opens, it has 50 pounds of bananas on a display table. Customers remove bananas from the display table at a rate modeled by f of t equals yada, yada, yada. for time 0 to 12, where f of t is measured in pounds per hour and t is the number of hours after the store is opened. After the store has been open for 3 hours, store employees add bananas to the display table at a rate modeled by g of t equals yada, yada, yada for t between 3 and 12, where g of t is pounds per hour and t is the number of hours since the store is opened. How many pounds of bananas are removed from the display table during the first 2 hours that the store is opened? So is the amount of bananas being removed constant? No, it's dependent on a function, dependent on t. So you're basically doing an accumulation, right? So this is just going to be the integral from 0 to 2 of f of t dt. How would I do that integral? I'm typing it into my calculator and asking it to do it for me. I'm not doing it by hand. Totally inappropriate to try to do it by hand. Use your calculator. Everybody's okay? And we've talked about how to do the integral on your calculator, right? You guys remember how to do that? So that's it for part A. For part B, it says find f prime of 7. Using correct units, explain the meaning of f prime of 7 in the context of the problem. How would I calculate f prime of 7? I'm typing it into my calculator. I'm not doing the derivative by hand. You could. I'm not. I will not have the time on the AP exam to do things by hand when I could do them with my calculator. You guys remember how to do the derivative at a point on your calculator? So if you just press the math button, you're going to be using the nderive command. So you just say with respect to x, type in the function, and then say x equals 7, and it does it for you. Not doing it by hand. Everybody's okay? What unit should this have? F of t is measured in pounds per hour, and t is hours. What's f prime of t going to be measured in? It's going to be pounds per hour, right? Just like if you take the derivative of velocity, meters per second, you get acceleration, meters per second squared, right? Same idea. And what is this representing? It's the rate at which the rate that bananas are removed at t equals 7, or something like that, right? Need to say it's the rate of a rate. Everybody's okay? C says, is the number of bananas on the display table increasing or decreasing at time t equals 5? Give a reason for your answer. Well, g of t is the rate in which the bananas are added. F of t is the rate in which the bananas are removed. So if I just subtract those two rates and look at whether it's positive or negative, I know the amount of bananas would be increasing or decreasing, right? So that would, oops. And then this is at a specific time, right? 5. You know, if it's greater than 0, it'd be increasing. If it's less than 0, it'd be decreasing. And this is your reason, right? It's just this calculation. Does that feel okay? And D says how many pounds of bananas are on the table at time t equals 8. So we started with 50 pounds of bananas, right? We remove the total of bananas over those 8 hours based on f of t, so that's the integral of f of t from 0 to 8. But we're also putting back bananas starting at hour 3 going to 8 at the rate of g of t. And then it's just, how am I doing those integrals? Calculator. I'm not doing it by hand, right? Nothing on this problem would I do by hand. If I have the access to my calculator, I'm never going to integrate or differentiate anything that's explicit by hand. If it's a calculator active problem, I'm just going to write down the setup and type it into my calculator. And as I've done here, where I've just referred to things as f of t and g of t and not written out the whole function, you are welcome to do that as well. The AP is fine with you doing that. Don't waste a bunch of time trying to write something down that's was defined as, you know, f of t or g of t or whatever earlier. Just write down what you did in your, you know, with that name and just be done with it. You guys are cool with seeing how this is still kind of the same thing as what we're doing with these force or these work problems. Instead of adding up a bunch of forces, we're adding up some other rate to get a total. It's the same concept though, right? And this is a very common presentation for the AP, is to give you something like this. All right, and then I have the last section in 6.5 is the concept of the average value of a function. So we know how to calculate the average value of some list of a finite number of values, right? You just add them up and divide by the number of values, just like you would in, you know, to calculate your GPA or anything else. But how do you compute the average temperature during a day if you have like infinitely many temperature measurements possible? Right? Like, what was the average temperature today? Well, there's infinitely many measurements you could take. How are you going to add those up? And that doesn't, seems like we need a new concept to do this, right? What do we do when we add up infinitely many things? What should that cue you as? It should be an integral problem, right? We're talking about doing an integral. If we're talking about having to add up infinitely many things, that's what the integral does, right? So this is the idea. We start by saying, okay, y is just going to equal some f of x, some function that represents our temperature, and that's over some interval from a to b, right? It's from like 8 a.m. to 8 p.m. or something. We'll divide that interval into n equal length subintervals. We'll call the length of those subintervals delta x. This is starting to sound familiar. We'll call the length of each subinterval. So then delta x is going to just be the difference of b minus a divided by n. And we'll choose a sample point from each subinterval. We'll call those x1, x2, x3, xn. And then average those values. And since n is also equal to, or since delta x was b minus a over n, we can say that n is equal to b minus a over delta x. So I throw that into the denominator instead. If I then like divide the fraction, I have 1 over b minus a times this big infinite sum. So I'm left with 1 over b minus a times the sum of those fxi's times delta x's, which that is our definition of an integral, right? We just now take the limit as n goes to infinity, and that's just the integral. So in general, the average value for that function is going to be 1 over b minus a times the integral from a to b of f of x dx. So just take the integral over the interval and divide by the length of the interval. That's all you're doing. So for example, if we want the average value of the function f of x equals 1 plus x squared on the interval from -1 to 2, we'd say that f average is 1 over 2 minus -1 times the integral from -1 to 2 of 1 plus x squared dx. So we just integrate as usual. So let's see, that's 2, 3, 17 thirds, 18 thirds. Oops, we still have that 1/3 though. So that comes out to be 2. Everybody's okay with that? So one way to think about what we just did now was we have our function 1 plus x squared looks like this, right? We have the interval from 0 to 2, or -1 to 2, I should say. And we have our average value as 2. What it means is that this area, that rectangle, is going to be the same as the area under the curve for that function. Right? If I take the average value of the function and times the length of the interval, that area will be the same as the integral, right? And in fact, that's what we say here in the next piece. The mean value theorem for integral says if f is continuous on AB, then there exists some number c on that interval a to b such that f of c is equal to the average value. And furthermore, that the integral from a to b of f of x dx is equal to the average value times the length of the integral. So exactly what we're kind of illustrating here, or that I just illustrated graphically. Does that feel okay? So it provides you another way, like to think about this. So here it says that since f of x equals 1 plus x squared is continuous on our interval, the mean value theorem says there's a number c on that interval such that the integral is equal to f of c times b minus a. So to find that c, what can we do? Well, we know what it is, right? This is f average, which we calculated to be 2 from the previous one, which tells us then the integral is just going to be 6, right? 2 times 3. And I don't want to do this. This is like more trouble than it's worth, to be honest with you. But that's the idea. So really just the big idea is this average value formula, which is just the area under the curve divided by the length of the interval that you're integrating over, which shouldn't be too surprising, right? Like, it's basically if I build a rectangle with the same area that has this fixed length, what's its height got to be? Well, that's the average value for the function. So that's it for chapter 6. Hopefully these last 2 sections didn't feel too bad. The accumulation stuff can be tricky because it's story problem, but conceptually there's not much going on there. There's not like a massive new concept or a piece that you really need to be able to visualize or like sneaky techniques for doing things. It just pretty much, if you understand like what an integral is doing, the setup is usually pretty easy. And then these average value problems are quite easy. I mean, it's just like doing an integral. So I want to talk about test format. I went and wrote the test yesterday. I haven't proofreaded it yet, so this might change a little bit, but this is essentially the outline here. So in the no calculator section, that'll be first. You're going to have 3 rational expressions to integrate. Remember, there were 3 different techniques we saw. Seems like you might see one of each. 2 problems where I ask you to find the area between 2 curves. I ask you to just do the setup only, so you don't actually have to finish the integral. You just have to like find the bounds and have the problem set up correctly. But you don't have to integrate. 4 volume problems. Again, setup only. So you don't actually have to finish the integral. You don't have to do any integration on part 1, aside from the rationals. The rational things you have to finish the integral for. But the areas and volume problems, you just have to do the setups. Everybody's okay with that? And this is me trying to be cognizant of time, right? I know time is often an issue. That should help speed things along where you don't have to grind through a bunch of algebra. In part 2, you're going to have 6 multiple choice questions, and then 1 FRQ style question, similar to the things you're seeing in the accumulation problems. Which again, I dropped those accumulation FRQs. There's 5 of them in there. My suggestion would be to do them. Like the one you'll see on the test will be almost the same as what you see here with minor modifications. But that's my test format. That I hope that sounds reasonable. I know the volume of rotation problems can be time consuming because you have to really think about the setup or whatever, but I think when I did do the proofread. I think I did this in like 22 minutes or something, the test, where it didn't take too long. I think that usually, that kind of 3 to 4 range is about where you guys work at. So this should be good. And if you know what to do, it should be very fast. But no pressure, right? Like you guys, right? Like you're not me. I've had the advantage of doing this all before a whole bunch of times where it's not new, so it's very easy. This is the first time for you, just like the first time for me, this was very hard. Or not easy, I should at least say. I know that you're in the same boat. But I want to emphasize, I tried to be mindful on this one, that the time was an issue the last time. So this is, I think I really tried to pare down at what I'm asking you to do and really only asking you to do the necessary things that are relevant to what we did specifically in this chapter. Notice that there's nothing specific average value. Where do you suppose that's going to land at? MCQs. Yeah. Yeah. Very, very likely that that's where the average value stuff will land. The good news is, though, what do you get for the MCQs? Calculator. So, like, even if you have to do an integral, who can do that for you? Your calculator. So, again, this test in particular makes sure that you're competent on using that to do integrals and derivatives and stuff, that just for a time standpoint, like for an MCQ, if you have a calculator, I'm not doing anything by hand unless I absolutely have to, right? If it's something that can be done with the calculator, if it's a definite integral or a definite derivative, calculator is going to do that for me. Only if it's like an integral will have the plus c in the answer am I going to do this by hand. Otherwise, the calculator is going to do this for me. And recognizing that will be helpful come AP time on what you can do with the calculator and what you can't, so you don't spend a bunch of time grinding something out by hand that's like a 30-second calculator problem, because you need those extra minutes for the stuff that you do actually have to do by hand. You can't spend that time doing things that you could do with the calculator by hand. So that's my plan there. For all of these no calculator problems where I ask you to find the areas and volumes, I will give you the picture. So I'll give you the graph of the functions. Not a three-dimensional picture for the volumes, but I'll give you a graph of the functions involved, so that you don't have to do that by hand. Also, that's I think is a huge time saver, that you have a decent picture from jump. So again, for those volume problems, we saw there's 4 different kind of volume problems, right? There's discs, washers, shells, and then like the geometric cross sections, where the textbook didn't have examples of those, but I put some extra stuff in from the my AP that has those kind of problems in there. I dropped in some additional MCQs here to the OneNote for you guys to look at along with the key there. I have the keys for the accumulation problems, and the rational function problems. I dropped in a key for that a day or so ago, so you guys can, as you're studying and looking over things, you can at least know when things are right and wrong. The accumulation key is like the stupid AP thing where it gives you like how they're grading it or whatever, which is sometimes a hassle to sort through where the answer is or how they got to their answer, but that's there for you, and we can certainly do specific questions, next class or whatever, if you run into some stuff you didn't like or you had trouble interpreting the answer from. Totally fine. But that's kind of it before this next test. You guys feel pretty clear as to like what you're going to have to do and what you need to study? Volumes is a big piece of it, right? That was like the most problems came from those volumes of rotation problems. So definitely want to make sure that you're good on like section 6.2, 6.3, 6.4, the areas and volumes. That's most of your part 1 are those guys. And then we did have quite a bit of stuff that wasn't necessarily textbook, right? The rational expressions wasn't a textbook thing. I didn't use the textbook. I just kind of like gave you some examples and some techniques, and we didn't use the textbook there. And the accumulation problems aren't necessarily textbook specific, right? So that's just to kind of remind you guys that there's a bunch of stuff that in this test that didn't necessarily correspond to things we did specifically in the textbook. Oh, and then like the geometric cross sections, again, wasn't specifically textbook problems. So there's a lot of AP stuff that I gave you guys in addition along the way. that I want to make sure that I feel pretty decent about. With some of these MCQs, I do have some like U sub stuff stuck in here also, because you need to, like, whenever we did any of these rational function problems that ended with a U sub anyway, so I just put some of those in the MCQs just to kind of make sure that you're fresh on that technique, because it's a sub routine in any of those rational function problems, or if you had to do anything else by hand. In general, not that you would for this test, but in general. So yeah, that's the format. Does that feel specific enough for you guys that, like, what to be looking over? Okay. Okay, yeah, that's the gist of it. I don't know that I have anything more to talk about necessarily. Do you guys have specific things for me right now, or are you just like, I just need some time to look over stuff before I even know what I don't know yet? Yeah, I get it. Okay. I will shut my yap and leave you guys alone then.